So now that we talked about the Executor framework at a very high level, let's spend a little time talking about the concept of thread pools, because in many ways that's what the Executor framework is doing. It's providing you with a pool of threads. And so we'll talk about the key features, we'll talk about the key benefits of thread pools. And I'll also give you a quite a very realistic notion of the concept of thread pools as we encounter them as everyday humans in our everyday lives. Concurrent programs often have to handle a large number of clients. So imagine a web server that has to handle lots of client requests simultaneously. I'm sure a lot of people who watched the Super Bowl last night, if you weren't able to watch the Super Bowl the whole time, you probably were looking at websites to see what the score was if you cared who won the game, or you wanted to see the halftime show redone or whatever. So in situations like that, like when it's the Olympics, people tend to hammer certain websites very heavily. And rather than having one core with one thread trying to handle hundreds of thousands of requests, people will typically have many threads and many clients. So one way to do this, not such a good way to do it, is to try to spawn a client per request. So a thread per client request is a bad thing. And that's because if you have 100,000 clients, you really don't want 100,000 threads. Very quickly, your computer will start to melt down. And the reason for that is that each time you spawn a thread, it takes up a certain amount of resources, typically allocates a chunk of virtual memory, usually about a megabyte worth of virtual memory, and you have to put a little entry in a data structure called the thread control block, and very quickly this gets out of hand. So you don't want to have one thread per client. It's kind of like if you went to a restaurant and you had like one waiter per person. That would probably get out of control, unless you're in a place where you have a lot of people who don't have a lot of, they don't have anything else to do, so they want to stand there and take your order. We'd just get out of control very quickly. Here's what such a program might look like. Were you to do it this incorrect and non-scalable way, you would have a method called handle client request that would be called back when a client request came in. And what you would do here is you would make a request runnable for that request, and you would start a thread. And that would very quickly spiral out of control. So you'd have a lot of extra memory. You'd have all these entries in the thread scheduling table inside the operating system. It would have to spend a lot of time managing that giant data structure. Just not a good idea. So even if it's possible to spawn threads, and on most operating systems nowadays you can spawn a lot of threads, it's probably not a good idea to do things like that in general. So what is an alternative? What's a better way to go? Well, a better way to go is probably to use a thread pool, where rather than having an unbounded number, or unbounded with respect to the number of clients, you bound the number in some way. And this, of course, is a win because it helps to amortize thread, memory, and processing overhead. And really, amortization is just a fancy way of saying that it sort of smooths out over time. You pre-spawn typically some pool of threads, or you let the threads be created on demand up to a certain maximum, and then you leave them around for a while, and as new requests come in, if there are threads in the pool, they go ahead and do their thing. If there are not threads in the pool, we'll see what happens in just a second. So here's kind of what the code would look like. So rather than doing this very inefficient approach, which was the thread per request approach, instead you can make yourself a thread pool with one of the various Executor methods. And then you can go ahead and when a request comes in, you can say, make a new request runnable for that request and execute that request. And execute does not run the request right away. Instead, what it does is it puts it onto a queue, typically. There's some variance of this we'll talk about later, but it typically enqueues the request, and then when a thread is available in the pool, it takes the request and runs it. Now, one of the big questions here, of course, is how big should that pool be? And we'll talk about that in just a minute, but in a nutshell, the decision about how big to make the pool depends on factors like how many cores do you have on the machine? Or are your tasks you're trying to run I/O bound or compute bound? And we'll talk a bit more about that as well. So there's a bunch of different factors that dictate what the size of the pool ought to be, ideally. And what you do is you typically, in most cases, you bind the thread pool to a work queue of tasks that are awaiting execution. So we'll typically have some kind of queue with runnables or callables in it, and the pool of threads coordinates with that queue in order to do the work. And you can probably already start to imagine real-world examples of these things, right? If you go to the airport to check in for a flight, you don't typically have one gate agent per person, right? I mean, imagine you'd have, if you had like it was a holiday rush season or the Super Bowl or whatever, you'd have like thousands of gate agents standing around handling each customer. That would get out of control. So instead, you have a pool of gate agents, and then you have a queue, literally a queue of people waiting to be served. And we'll talk about some other known uses here in a second. You can think of the worker threads as being like hungry puppies. They sort of sit around the bowl waiting to be fed, and when new work comes in, the next puppy in the pool wakes up and goes ahead and does its thing, eats the work and does some processing. Let's talk briefly about human known uses of thread pools. I used the example of going to the airport. That's one example. Another good example would be a call center. So chances are at some point you had to, make a flight reservation or a change to your flight reservation, or you needed to call up to find out about, your credit card, if you have a credit card, or, if you have to deal with the Internal Revenue Service, you have to call up and ask questions if there's something wrong with your taxes or whatever, right? Sometimes you have to call up to a call center. And in that environment, there's going to be a pool of operators standing by, which I always thought this was clever. Operators are standing by. Do you get it? It's like C++ or C operators, arithmetic operators. So the operators are standing by. There's a pool of them. There's obviously not one operator for everybody calling in. And invariably, when you call a call center, you have to go through a menu, and then eventually you get put in queue, and it says something like, calls will be answered in the order received, so don't hang up and try again. So there's obviously a queue of calls, and there's a pool of operators, and they're responsible for handling the calls. So that's a good example of a human known use of all this stuff. Okay, so that was a quick overview of thread pools in general. Now, of course, in the next lesson, we'll talk about Java thread pools.